The center of our galaxy is nearly 30,000 light-years away, but it's 20 times closer than the center of the nearest galaxy and hundreds of times closer than galaxies like Andromeda. So we know more about the center of our galaxy than the center of any other stellar system in the universe. It's been known for decades that interesting things are happening in the center of our galaxy. The normal view of the center of our galaxy occurs best from the southern hemisphere. In North American latitudes, it's hard to see the galactic center. It's down in the murk, low in the sky. From the southern hemisphere, it presents as a ragged mass of dusty lanes chopping up the star fields, with a great stellar pileup near the constellation of Sagittarius. That's the location of the galactic center. The cleanest view of the galactic center comes from infrared observations. These were only possible 30 or 40 years ago as infrared detectors matured. Seen in near-infrared light, the galactic center shows up as a dense star cluster, the stars almost appearing to overlap. Infrared radiation travels freely to the galactic center without being obscured or affected by dust. Observations at other parts of the electromagnetic spectrum affirm that something interesting is happening in the galactic center. Radio observations show on large scales of hundreds of light years striations caused by spiraling electrons in magnetic fields. This electron acceleration has a source that's unknown, but is associated with the dynamical and mass center of our galaxy in Sagittarius. As the technique of interferometry was applied to the galactic center using radio telescopes, radio astronomers were amazed to find an incredibly compact radio source exactly at the galactic center. To date, it is still the most compact radio source ever discovered. It's not been resolved even by the largest interferometers. The source of this radio emission is also not understood. Additional indications of something interesting going on in the galactic center come from X-ray emission, which also exists more than would be expected from high-energy stars, and electron-positron annihilation emission. Observation of that kind of radiation has poor angular resolution, so can't be uniquely associated with the very center of our galaxy, but almost certainly is going on there. So we have a conjunction of pieces of information indicates something beyond normal stellar astrophysics is going on at the center of the Milky Way. The most exquisitely detailed observations of the center of our galaxy started coming in the 1980s as people used the adaptive optics technique and infrared observation to home in on that central star cluster. With detailed observations, it was possible to isolate individual stars in that star cluster and follow their actual motions in space over time. As the observations accumulated over the first decade, astronomers were intrigued to watch the Keplerian orbits of individual stars around the center of our galaxy, in a region only light days or light weeks across. It's possible to take this data and look at animations which show that some of the stars appear to be whipping close and fast by the central object, whatever that might be. With Keplerian orbits observed for individual stars, each one can deliver a mass estimate for the central object, and the sum of dozens of these observations has given us an extraordinarily detailed picture of the mass of the center of our galaxy. The number calculated has varied over the years as the samples have changed, but is roughly 4 million times the mass of the Sun. So, something exists that's 4 million times the mass of the Sun that's concentrated in a very small region, less than a few light weeks across. What could it be? Two groups working in friendly competition produced the data to define what went on in the center of our galaxy. A group led by André Ghez at UCLA using the Keck telescope, and a group in Germany led by Reinhard Genzel using the European Southern Observatory in Chile. Both groups agreed on the answer they got. The method is basically to calculate the stellar motions on increasingly small scales towards the galactic center, and then deduce what could possibly be causing such motions. Essentially, we're calculating the mass density on smaller and smaller scales. A graph of the enclosed mass density is then compared to the conventional model of what might be going on. We know there's a star cluster there, and it's possible by dynamical arguments to figure out what the maximum stellar density of a star cluster could be. Nature does not have a way of piling more than a certain number of stars into a small volume because they are given such large motions by the mass that those motions take them away from the center. In the analysis, the dashed curve represents the maximum enclosed mass from any star cluster at the galactic center, whereas the data points show the enclosed mass measured by those individual stars in their Keplerian orbits. Clearly, the best distinction of what's going on comes from the stars that travel closest to the very center. Those probes have now been taken towards only light days distance from the very center of the galaxy, which is defined typically as the ultra-compact radio source. The result is dramatic. The enclosed mass does not decline as you move in by orders of magnitude from light months to light weeks and then to light day scales. The enclosed mass, a few times a million solar masses, is orders of magnitude more than can be explained by any star cluster. The only possible explanation is a massive compact dark object, a black hole. By the late 1980s, the supermassive black hole hypothesis for what's going on in the galactic center was becoming widely accepted. Now astronomers want to know more about this amazing object only 30,000 light years away. X-ray observations have shown variations in the X-ray emission from the very central region. X-ray flares that are actually associated with the black hole ingesting matter, perhaps swallowing stars whole or digesting lumps of gas falling in. That's inference. We don't have high enough resolution to see what's going on very close to the putative event horizon. A steady zoom in will show what astronomers have revealed in the central regions of our galaxy on successively smaller scales. An animation of a decade's worth of data from the Keck UCLA group shows the exquisite nature of these stellar orbits, and the fact that some of them pass quite close to the event horizon. Not close enough. Clearly, with deeper observations and better adaptive optics, the odds of finding a star that passes extremely close to the event horizon are large. And in fact, the goal of astronomers doing this work is to find a star that passes behind the event horizon, allowing the light to be shadowed by it, and allowing us to see the extreme effects predicted by general relativity. It will require some luck to find such a star, but if we were able to double or triple the samples that are currently observed by going to fainter stars, the chances are we'll get lucky. The Galactic Center is unexceptional to the naked eye in invisible light, but in other regions of the electromagnetic spectrum, it's clear something extraordinary is going on. There's an extremely dense star cluster seen in infrared light, an ultra-compact radio source, high energy and variable X-ray emission, and even the emission from the annihilation of positrons and electrons very near the center. Dynamical observations of individual star orbits very near the galactic center within a few light weeks have allowed us to calculate the mass at that very center, and the number is about 4 million solar masses. The mass density is far too large to be explained by any normal cluster of stars. The only plausible explanation is a supermassive black hole, and the hope exists in the near future that we might be able to probe regions very near the event horizon and test general relativity in new ways.